So far, every solution we've found has had that arbitrary constant in it, that c. Sometimes that's fine, but sometimes we have enough information that we can lock down the c as well. So let's take a look at an initial value problem. That's what these things are called, initial value problem, where they actually know at least one point that the original function goes through. So our first step is going to be to solve the differential equation like normal, and then we'll try to see if we can figure out that plus c with the given information. Okay, so let's see about this thing right here. Let's see if it's separable, first of all. I'm going to go ahead and multiply both sides by x just to start. I know that doesn't totally separate things, but it gives me a little room to write my dy dx. Okay, so if I divide both sides by y and multiply both sides by dx, dy over y equals 3x over x squared plus 4 dx. Okay. Now we're happy. We've figured out that it is a separable differential equation. It means we can go ahead and integrate both sides. One's an integral in dy, the other one's an integral in dx. We know this side is 1 over y, dy. This side over here actually looks like it's going to need a little u substitution. So let's go u equals x squared plus 4. Du equals 2x dx, and let's see, it means 1/2 du is going to be x dx. Maybe I'll go ahead and move this 3 out front so it looks like just x dx right there. Okay, so rewriting this side in terms of u, oops, got the 3 out front. X dx, same thing as 1/2. And maybe I'll move the 1/2 out front as well. 1/2 du. X squared plus 4 is u. So I moved everything away, so there's a 1 on top of that. Okay, I think we're actually ready to integrate both sides now. So 1 over y goes to natural log of y, and this becomes 3/2 natural log of u, and I'll go ahead and replace u with x squared plus 4, and then don't forget that plus c. It's solved. The differential equation is solved. I haven't yet solved for c, but I can do that right now. I know that when I plug in 0 for x, I should get 4 for y. So I should be able to go ahead and plug that in. Here, let's do it over here. So natural log of 4 equals 3/2 natural log of, plug in 0 for x, 4 also, plus c. Subtract 3/2 natural log of 4 from both sides. And that is actually going to give you negative 1/2 natural log of 4 equals c. And, okay, so we know c. Sorry, let's go back to the original differential equation here. And we can fill in c now as minus 1/2 natural log of 4. Okay. Again, basically done, except for we often like to see these things actually solve for y. So again, let's exponentiate both sides, keeping in mind that's all going to be exponent. So this becomes y equals. And I know I can separate this into two. Oops. Okay, so separate that into two exponents multiplied. E and natural log don't cancel each other out if there's something in between jamming the gears, like this 3/2 right here and that -1/2 right there. Fortunately for us, we know an algebraic property of natural logs, which says we could move those up there and make them exponents. So we can get y equals e to the natural log of x squared plus 4 to the 3/2 times e to the natural log of 4 to -1/2. Now the e's and natural logs can cancel each other. So finally, we're finally here. Our solution is x squared plus 4 to the 3/2 times 4 to the -1/2. I'll just put it right there for 4 to the -1/2 is 1/2. So I could rewrite that as okay, and we're finally done with that initial value problem. When you plug in 0, you should get 4. So 0 plus 4 is 4, square root of which is 2, cubed is 8, half of that is 4. Okay, plugging in 0 does give you 4, and presumably if you took the derivative of the function, divided that by x, it would be equal to 3 times the function divided by x squared plus 4. Let's not check that. Okay, let's do one more initial value problem. Okay, so here's another one. Again, we hope that it is separable. So let's get on the right layer. Let's write x times dy dx plus y equals y squared. It's not immediately obvious to me how to separate this, but I'm just going to start doing a little bit of algebra and see what happens. I'm going to move the y to the other side. Okay, I think I can see it now. Also multiply both sides by dx. Notice this is not separated yet. I still have x and dy on the same side and y and dx, but we're getting there. Divide both sides by y squared minus y. Also divide both sides by x. So we'll get dy over y squared minus y equals dx over x. We really don't know how to integrate with 1 over dx, so we can't put dx on the bottom, unfortunately. That would make the rest of our work easier, but we have to keep dx and dy on the tops of their respective fractions. So the integral that we're going to try to do here looks like 1 over y squared minus y dy. And 1 over x dx. The 1 over x is pretty easy to integrate. That just goes to natural log of x plus an arbitrary constant. The 1 over y squared minus y is a little more difficult to integrate. And you may be thinking of something you don't want to be thinking of, but it's the right answer. Partial fractions is what we need here. And we know how to do partial fractions. I'm not going to run through the steps of doing partial fractions. I'm just going to jump straight to the answer here and say the partial fraction separation here is 1 over y minus 1 minus 1 over y dy. And now we can integrate those two pieces pretty easily. This becomes natural log of y minus 1 minus natural log of y. And you know the properties of natural logs allow us to combine those into natural log of y minus 1 over y. Okay, so we've integrated, we technically have a solution. As usual, it is not actually solved for y. I could take a moment here and plug in 1 for x and negative 1 for y and solve for the c. I think at least this time around I'm going to just leave c as c. That's a little easier to write down than like natural log of 1/4 or something. So I'm going to actually solve for y first, and then I'll figure out the c afterwards. So let's exponentiate both sides. On the left-hand side, e and natural log cancel each other directly. On the right-hand side, I'm going to separate into e to natural log of x, e to the c, and we know that this becomes e to the c is a constant, and e and natural log cancel each other, so that's x times a constant, or actually somehow I feel more comfortable with the c in front, so we'll do it that way. I'm still trying to solve for y here. It may be a little bit easier now to separate this into y over y minus 1 over y, so we'll get 1 minus 1 over y. I'm going to add 1 over y and subtract cx. I'm going to multiply both sides by y and divide by divide by 1 minus cx. Okay. All that work, but a fairly simple solution. We do still need to figure out the value of c so that our solution goes through the point 1, negative 1. So when you plug in 1 for x, you get negative 1 for y. So let's make that happen. Let's plug in negative 1 for y and say I need that to be 1 over 1 minus c times x. So negative 1 needs to equal 1 over 1 minus c. You can do a little bit more work, but that ends up being that c equals 2. So my ultimate answer to the initial value problem that specifically goes through the points that they wanted us to go through is 1 over 1 minus 2x. There it is. Simple enough. All right. In the next video, we're going to look at a couple applications of this type of differential equation.